Example 2. Here is another flow diagram. What is the maximum flow of this network? Now what we're going to do is we're going to do the same similar sort of method that we did before, where we were just marking all of the different pipes and how much can go through, although I'm going to do it slightly differently. You might remember in the previous one, I was just sort of tallying and seeing how much could add up in each one. I'm going to do a slightly different method, which is called the uppermost algorithm. The uppermost algorithm is the same procedure as we did, but instead of just saying like 8 out of 10 or 7 out of 10, we do some subtractions. And I'll show you what I mean by that. So this pipe, as just what I like to do is I like to sort of indicate what's the biggest amount so I know where I should be aiming for. The last two edges here add up to 21. The opening two edges add up to 22. So that means that the maximum flow can't be bigger than 21. It's most likely to be much smaller than that. So let's have a look. So the uppermost algorithm means that I start by eliminating all of the edges from the uppermost flow down to the lowest. The uppermost flow I'm highlighting now in yellow. When I'm doing the uppermost algorithm, what I do is identify the smallest edge, or in this case it's 7, and then I subtract that number from all of the others. Once I've subtracted it, any edge that is marked with a 0 is immediately eliminated. So that pipe marked 7 is now been eliminated, and if there's any other pipes or any other edges that only go into that edge there, they can also get eliminated. So this one that's been marked 9 take away 7 equals 2, because that edge cannot be diverted in any other way, that also gets eliminated. The first source that I've done 10 take away 7 equals 3, that can get diverted, so we won't eliminate that one yet. Similarly, the 11th take away 7 equals 4 at the very end, sewage can flow, or whatever the item is can flow through from another way. If you like, another way you could also read this 10 take away 7 is that 7 out of those 10 liters have been accounted for. So they've been accounted for and spread out this way. So we've got 3 more liters to play with. This is the next highest flow that we can do. So we need to eliminate the smallest number. The smallest number is either 3, 5, or 4. 3, remember, is what that first source has become. 3 is the smallest number, and so we will subtract everything by 3. We have done the subtractions, and we notice that that first edge there that was originally at 10 is now at 0, so it has been eliminated. What we can also do is eliminate any edge that came off from this pipe or from this edge because it can't be diverted. So for example, this one marked 7 and this one marked 5 minus 3 equals 2. They directly came from this edge, so they too are eliminated. The next highest pipe that we can use is this one here. So it's starting from going down this particular way using the 12, starting from this 12. So we go from 12, 8, 4, and then this 1. So the smallest pipe or the smallest amount that we got is this 1. So we'll subtract everything by 1 and eliminate any edge that is equal to 0 or any edge that connects to that 0 pipe. Because this pipe here, or this edge here, I keep saying pipe because of the previous example, I'm sorry. This edge here that had 11 to start with, 10 of its liters were accounted for by the other method, by going up the first edge. Only 1 more liter was to spare, so we've taken 1 liter from the bottom flow and it's gone through, and now this whole edge here has been accounted for. And any edge that could only flow into that has now been crossed off because we're now at full capacity. So the 7 here, the 3 here, this edge here, this edge, and this edge are all accounted for. So therefore, or we can't flow through those anymore. So we eliminate them, which means we have one more path that we will then do a subtraction with. So in this last path, we've got 11, 10, 8, and 10. Remember, the 11 was because we subtracted 1 from earlier. The smallest pipe length is 8, so we should subtract 8 from each of these. So we have now eliminated all of the edges. You could possibly deduce how many from each path that we have that will determine the maximum flow. So for instance, we used 10 of the first one and we've used a total of 9 from the second. But one way you could do it arithmetically is something like this. So by taking the original edge weight and we subtract the final edge weight, and there are for both of these initial edges, and adding in that final answer, we get how many is the total, the maximum flow that can get through this, which is 19, whatever it is, liters or whatever the case might be. Example 3. A cut to a flow diagram is a line, a dotted line, that passes through the edges. It separates the source from the sink. The capacity of the cut is found by adding edges of a certain direction. I know that cut A has a capacity of 33, cut B has a capacity of 28. Explain how each capacity was found, hence or otherwise calculate cut C, which is for some reason called the minimum cut, and explain how it might relate to the network flow. This network is the same network that we dealt with before. So when we're cutting, it's separating the source from the sink. One of the things that I do when I try to calculate a cut is I highlight one side. In this case with cut A, I'm going to highlight the side of the line that suggests the sink. The white side or the blank side is the source side of the cut. And then the yellow side is the sink side of the cut. In other words, it's where we are, if you imagine it's like a little border that separates the source from the sink. So all we need to do is we now just need to cut any edges that are pointing from the source side into the sink, or as I like to do, from the blank side into the yellow side. So for example, with cut A goes through this edge here that's marked with a 12. 12 is pointing from the blank side into the yellow side. This edge here marked with a 7. This is going from the source side into the sink side. This one marked 5 is going from the source side into the sink side. I'm looking at the direction of the arrow here. And 9 is pointing into this, this 9 here is pointing into the sink side. So therefore, that one is counted. So why am I picking these ones? Because these are where this cut cuts through. So this cut touches each of these edges. So all I need to do is to add those together. 12 plus 7 plus 5 plus 9 gets me 33. I will do the same thing, but for cut B. So you'll notice here I've only circled 4 out of the 7 edges that this cut B touches. This is because the one marked with 8 and the one marked with 6 is going from the yellow side back into the white side, so it's going from the sink to the source. So we do not need to include those when we're counting the cut. So with cut C, I did the same technique, which is I just highlighted the sink side, and you'll see there I've just circled 8 and 11. And the reason is that those are the only ones where the edges are pointing into the yellow side. The one marked with a 7 here is pointing the other way. Now, why this is useful is that this is a minimum cut. If you find the minimum cut of a flow diagram, you are able to find the maximum flow. So the minimum cut will always give you the maximum flow. I am not very good with my visual sort of shaping things out, so I rarely go with the minimum cut. Some people can just see it, but I also struggle putting a couch in a lounge room. So, if you can see where the minimum cut should be, please go ahead and use it. But I have given you 3 strategies to be able to find the maximum flow. And in the next page, we're going to go through some examples of which ones are which. I would suggest that if you look at the next examples, to pause the video and give them a go, and then check to see if you're correct. Example 4. In the graph above, we need to find the capacity of the cut shown. Similarly with example 5, in the graph above, which one of the following cuts has a capacity of 27? I would suggest doing the highlight strategy to be able to solve for each. So the answers for example 4 would be C, 21, and for example 5, it's D, is the one that gets you a cut of 27. Examples 6 and 7 refer to the network below. In this example, you can see, you can assume that this final vertex is the end. Example 6, we need to find the maximum flow possible from A to G. And example 7, when the maximum flow is occurring, the flow from D to E is. You can use any of the strategies that I've taught so far to find this result. So we can see there that the maximum flow would be 14 by just showing how many is going through each edge, and showing the maximum flow or calculating the maximum flow, then yes, from D to E, that maximum is 4. Don't fall into the trap of just thinking that because that edge says 4, that the maximum flow can be 4. Yeah, a question says when the maximum flow is occurring. So for example, if it had said from E to the end, the maximum flow would have been 5.